Imagine a future where robots not only perform tasks, but also understand and respond to the world around them. In this video, we're going to explore the 6 phases of artificial intelligence in robotics, each representing a pivotal moment in the transformation of machines. The first phase can be known as pre-programmed robots. In the early days of robotics, before the advent of sophisticated artificial intelligence systems, pre-programmed robots reigned supreme. These robots were the pioneers, taking the first steps in the long journey towards more intelligent and autonomous machines. At this stage, the field of robotics was in its infancy, and the limitations of technology were evident. Pre-programmed robots perform simple tasks and can only do one thing. These machines were defined by their singular purpose. Pre-programmed robots were, as the name suggests, precisely coded and configured to execute specific tasks. Their actions were determined by a set of instructions meticulously input by human operators. These instructions left no room for interpretation. Every movement, every action was scripted in advance. As a result, pre-programmed robots lacked the flexibility and adaptability that we associate with more advanced robotic systems today. These early robots were highly specialized and designed for repetitive and predictable tasks. They thrived in controlled environments such as manufacturing assembly lines, where precision and consistency were paramount. Consider the classic example of a pre-programmed robot, the mechanical arm on an automotive assembly line. This mechanized limb had a singular mission: to weld a car door, insert a specific engine component, or execute another task within the production process. Its relentless pursuit was efficiency and consistency, far surpassing human capabilities in terms of speed and stamina. However, these robots operated within a world largely devoid of artificial intelligence enhancements. They functioned without the cognitive flexibility that characterizes more advanced robotic systems. Instead, their actions were scripted, their responses rigidly determined. They were incapable of responding to unforeseen changes in their surroundings, which limited their utility in dynamic and unpredictable environments. Despite their limitations, pre-programmed robots played a vital role in industries where precision and consistency were paramount. They showcased the potential of automation and paved the way for the development of more intelligent, flexible, and adaptable robotic systems. Their importance in the history of robotics cannot be overstated, as they laid the foundation for the robotics revolution that would follow in the subsequent phases of artificial intelligence integration. These early robots were the first steps towards a future where machines would possess the intelligence and adaptability akin to humans. The evolution of robotics took a significant stride forward with the emergence of reactive machines, marking a transition from the rigidity of pre-programmed robots to a new level of responsiveness and adaptability. The second phase can be known as the reactive machine phase. Reactive machines represented a crucial phase in the ongoing evolution of robotics, as they introduced the concept of limited intelligence and the ability to react to specific stimuli. At this stage, robotics moved beyond the purely deterministic and rule-based behavior of pre-programmed robots. Reactive machines were designed to respond to predefined cues, allowing them to execute tasks with a semblance of intelligence. While their responses were still based on rules, they demonstrated a level of environmental awareness that was absent in their predecessors. One of the hallmark characteristics of reactive machines was their reliance on sensory inputs. These inputs, often derived from sensors or cameras, enabled the robot to perceive its surroundings in real time. This perception served as the foundation for decision-making, as the robot could assess its environment and react accordingly. For example, devices like voice-activated thermostats or virtual assistants can respond to voice commands, adjusting the temperature or providing information based on predefined rules. While their responses were rule-based and predefined, they represented early examples of reactive machines. Reactive machines found applications in various fields, particularly in tasks that required responsiveness to specific cues or stimuli. For instance, in the automotive industry, reactive robots equipped with sensors could detect anomalies in the manufacturing process and adjust their actions accordingly to maintain product quality. These robots offered a degree of adaptability, making them suitable for tasks where predictability and repeatability were essential. However, it's important to note that reactive machines still operate within a predefined set of rules. They lacked the capacity for learning or adapting beyond those rules, which limited their utility in dynamic and evolving environments. In essence, they were designed to react, but not to learn or reason beyond their initial programming. Reactive machines represented a crucial phase in robotics, as they marked the point where machines began to exhibit traits associated with intelligent behavior. While they were not yet fully autonomous or capable of learning from experience, they represented a significant step towards more intelligent and adaptable robotic systems. This phase set the stage for further advancements in robotics, particularly the integration of learning and adaptability in the subsequent phases of development. The third phase in the evolution of robotics introduces us to teleoperated robotics, marking a significant leap in terms of remote control and human-machine collaboration. Teleoperated robots are semi-autonomous machines controlled by human operators from a safe distance using a wireless network. These robots usually work in areas where it's challenging or unsafe for humans to be physically present. Examples include teleoperated robots like the Mars rover, robotic surgical systems like the Da Vinci surgical system, and remotely controlled submarines. While teleoperated robots extend human capabilities, they still rely heavily on human guidance. Phase 4 is autonomous robots. The advent of autonomous robots represents a watershed moment in the field of robotics. These machines can operate independently, making decisions based on their own sensory inputs and internal algorithms without direct human control. Autonomous robots rely on advanced technologies such as artificial intelligence, machine learning, and sensory fusion to navigate and interact with their environments. Examples include autonomous delivery robots and robotic vacuum cleaners. While they face challenges like safety and ethics, their potential to revolutionize industries and enhance efficiency is undeniable. The fifth stage in the evolution of robotics introduces us to humanoid robots, a remarkable fusion of cutting-edge technology, biomechanics, and artificial intelligence. Humanoid robots are designed to mimic human form and capabilities, marking a significant departure from the mechanical and utilitarian designs of their predecessors. At this stage, robotics aims to bridge the gap between machines and humans, enabling robots to interact with our world in ways that were once the stuff of science fiction. One of the defining characteristics of humanoid robots is their human-like appearance. They possess a body structure that includes a head, torso, arms, and legs. This design enables them to perform tasks in environments built for humans, making them versatile in applications that require interaction and mobility. Humanoid robots are often equipped with an array of sensors, including cameras, microphones, and touch sensors, allowing them to perceive their surroundings and interact with humans and objects in a more natural and intuitive manner. These robots often incorporate natural language processing capabilities, enabling them to understand and respond to spoken languages or gestures. This breakthrough in human-robot communication fosters seamless interaction between humans and machines. For example, humanoid robots can engage in conversations, recognize faces, and respond to questions or commands, making them suitable for customer service roles, educational settings, and various forms of entertainment. The mobility and dexterity of humanoid robots are another hallmark feature. They can walk, run, climb stairs, and perform tasks with a level of grace and precision that resembles human movement. This mobility allows them to navigate complex environments and execute tasks that require physical interaction, such as carrying objects or assisting with various chores. Notable examples of humanoid robots include Pepper by SoftBank Robotics and Sophia by Hanson Robotics. Pepper is widely used in retail environments and customer service roles. It can interact with customers, provide information, and offer a personalized experience in stores and public spaces. Pepper is also used in educational settings, including language learning programs, where it assists learners in improving their language skills. Sophia, on the other hand, is designed for social interaction and has garnered significant attention as a humanoid robot with a lifelike appearance. Beyond its social role, Sophia is also used for research and AI development, pushing the boundaries of what robots can achieve in terms of human-like capabilities. Humanoid robots represent a significant advancement in both robotics and artificial intelligence. They push the boundaries of what machines can achieve in terms of human-like capabilities and interaction. Their versatility makes them suitable for a wide range of applications, from healthcare assistance and customer service to entertainment and research. As technology continues to advance, humanoid robots are likely to become even more sophisticated and integrated into our daily lives, further blurring the line between humans and machines. The last phase is augmenting robots, which represent a transformative leap in the integration of machines and humans. These robots are designed not to replace humans, but to enhance our capabilities, working collaboratively with us in various domains. Examples include robotic prosthetic limbs and exoskeletons that bestow humans with enhanced strength and mobility. Augmenting robots promise to reshape our understanding of human potential, where our potential knows no bounds. The future of robotics holds promises of even greater innovation and integration with our daily lives. These machines are not here to replace us, but to complement and enhance our abilities, pushing the boundaries of what's possible. If you found this journey as fascinating as we have, don't forget to subscribe and hit that notification bell so you won't miss any of our future explorations into the world of technology and beyond.